Okay, then you will not be able to call that as a resonance because the system is not even oscillating. Okay, when omega square is negative, okay, what happens is omega becomes imaginary, right? When
Yes, sir.
omega square is negative, omega becomes imaginary, but you have e power omega t. So if omega becomes imaginary, what happens? It's e power minus alpha t, right? When omega becomes imaginary, there is already an I here, so I times I is negative. Okay, it's e power minus alpha t, and
Yes,
then
sir.
it's this solution. Okay, does it make sense?
Yes, sir.
Okay, so when omega becomes negative, which means if s over m is smaller than r square over 4m square or 2m square, okay, if this is the case, then there will be no oscillations. Okay, or rather I would say at the resonance there will be no oscillations. Where the resonance happens, there will be no oscillations. The resonant frequency will not correspond to an oscillatory solution.
But the imaginary solution which you told right now, like just a while before, so what do we call them? Like critically damped, critically damped oscillation or something.
Which solution you mean?
Like the flat one.
This flat one? Oh no, this is not critically damped. I wouldn't say that. I wouldn't say that. I don't know what to call this.
Sir, hello,
Uh-huh.
sir.
Yeah,
Sir,
yeah.
then, sir, there is a possibility in our universe that some of the particles which
Hmm.
can behave like this, sir,
Yes, absolutely, absolutely,
but
absolutely.
we can't detect that yet, sir.
No, okay. That so I know where you're going. Okay, let me come back to that. But before that, the first question, the first guy who asked the question, the velocity resonance. Velocity resonance happens when velocity resonance happens. Power gets transferred to the oscillator maximally. Okay, so velocity resonance corresponds to power transfer. Corresponds to power transfer. If you want to transfer power to a system, if you want to transfer power to a system, you need to, it'll be better if you choose a frequency where that system can absorb the maximum power. Does that make sense?
Yes, sir.
Okay, so this condition is so important for all power transfer mechanisms. All power transfer mechanisms. Let's say you're mm, there is wireless power transfer coming up. Have you guys heard of that? Have you
No,
guys
sir.
heard of the wireless power transfer? Like you have your the phones. You're charging your phones with a wired card, right? Why do you need wires? The tangling wire. Why do you need that? You can just have some radio frequency from from a source, and then let your phone access that radio frequency, targeted radio frequency like laser. Why can't you do that? You can do that, right? There is a lot of research going on about wireless power transfer.
So like
Okay,
wireless chargers.
I'm sorry.
Wireless
Yeah, wireless.
chargers are
Yeah, exactly. Yeah, wireless chargers. Yeah, exactly. Wireless chargers. Okay, there that power transfer happens only when you have velocity resonance. You need velocity resonance there. Without velocity resonance, you cannot transfer maximal power. Okay, you have electrical cars, and these days they've been experimenting with it. So basically, you have ropes, and the cars are electrical. So no, there's only two or four, whatever. So you have this induction coils. Okay, and when the car comes over the induction coil, the car gets automatically charged. Okay, so basically, as you drive on the road, the car gets charged, certain sections of the road. And this is being experimented as we speak. Okay, the battery of
So
a car. Hmm?
if I want to know, like, how they get charged? Like, I have heard that if we drive the car on the road, the battery gets charged automatically.
Yeah, it's just magnetic induction, right? You have an RF frequency that is coming off of the road. You have coils embedded in the road. Okay, there are coils embedded in the road, and you pass certain oscillating current, AC current, through the coil, and it creates a magnetic induction. Okay, and the magnetic induction is coupled to a battery or to a power source, and because of this magnetic induction, there is going to be a current here, and that current can be stored. A voltage, sorry, not a current, a voltage, and that voltage can be stored. That power can be stored. It's just due to magnetic induction. Right? It's the same magnetic induction that opens doors. If you're in an apartment complex, many apartment complexes, maybe not in India, but many apartment complexes have automatic gates. The gates are automatic. So once a car comes in, there is this little magnetic strip in the bottom, and when the car comes in, the magnetic, the flux, or rather the permittivity changes. Okay, so that is detected by the coil on the ground, and the door automatically opens. Okay, this is common. This is commonplace in many apartment complexes in the West.
Okay, so like shopping complexes also has this feature, like
Yeah, possibly. Yeah,
yeah.
yeah. It's automated. Yeah, but only with cars. If you walk, nothing's going to happen because you do not change the permittivity of the loop so much. Okay, so this kind of behavior, this kind of thing happens only with velocity resonance. You have maximal power transfer. If you want to charge wirelessly, you need to have velocity resonance between the two, the emitter and the absorption system. You need to have velocity resonance. That's when you have maximal power transfer. Okay, and that is why velocity resonance is important. Okay, displacement resonance is important where you don't want maximal displacement, like in earthquakes. Okay, in earthquakes, there can be displacement resonance. It's actually beautiful because when I say beautiful, I mean so there are, when there is an earthquake, there are patches of lands which are completely demolished, and there are patches of lands which completely are unscathed. Nothing happens to them. There are places where everything falls down, and there are places where nothing falls down, and that is because of resonance. It depends on the ground conditions. Like if this ground is loosely packed and oscillate at a lower frequency, and if this ground is tightly packed and oscillates at a higher frequency, then they have different resonance conditions, right? The frictional, sorry, the spring coefficient for this loosely packed soil and the tightly packed soil are different. The S is different for this and this. This is tightly packed, right? They are completely different. So if the oscillating frequency of the earthquake matches one of these is going to be destroyed completely. The other is going to be left unscathed because there is no displacement resonance. Do you understand that?
But very much probable that loosely packed will fall first because the foundation is not so strong.
Actually, no. Actually, no. Because loosely packed can have. See, let's say there is a loosely packed patch here, and let's say there is a loosely packed patch here. The wave comes through here. What happens? Okay, so the wave gets, a lot of energy of the wave gets dissipated right here, and nothing gets through here. Let's say, what happens then? Okay, the tightly packed structure. I'm sorry.
First patch will be destroyed, like
Yeah. The ones that encounter the waves first will be destroyed. The rest of them will stand because the energy got dissipated early. It's like some parts are behaving like shock absorbers. The rest of them are completely intact. Whereas for tightly packed, the whole area will shake because there is no dissipation. Right? This is complicated. Okay, I'm just, it's a caricature. What I'm doing is a caricature. It's a complicated business, but depending upon the tightness, depending upon the type of soil, depending upon the type of rocks present in the area, the earthquake can have different effects, and that is due to displacement resonance. Okay. Okay, tightly packed places can oscillate for long distances, much larger distances can oscillate coherently, whereas loosely packed places, they don't have to oscillate coherently because they are loosely packed. Okay, so these are extraordinarily important. These velocity resonance and displacement resonances are extraordinarily important when it comes to applications. Okay, you need to be always watchful for resonances. I love telling this story to my previous classes. So one of my friends, he had a car, maybe an old car, like we were grad students. Obviously, grad students did not have enough money, so we got cheap cars. And so whenever he drove the car, at other times the car would behave perfectly all right. But when he drove exactly at 90 miles an hour, okay, the car would shake. The wheels would shake. His driving wheel would shake. It'll vibrate. It starts vibrating. And if he passes 100 miles an hour, nothing happens. Then again, everything is quiet. Okay, we used to drive together, and he keeps complaining. Okay, why does damn thing happen? He's an economist, a marketing guy. He probably knows resonance, but maybe he didn't recall it. So right at 90 miles an hour, the car starts shaking, and he complains, "Oh, why the damn thing does that exactly at 90 miles an hour?" Because basically 90 miles an hour is the perfect speed for traveling on highways in the US, right? So he keeps complaining. I told him, it's resonance, basically resonance. Somewhere, some part of the car basically resonates at this exact frequency. And that's why the wheels are vibrating just because of that. Okay, so it occurs everywhere. It's everywhere. So you need to be watchful for those resonant behaviors. Sometimes resonance can be helpful. Sometimes, many times, resonance can be dangerous. Okay. As for non-detectability, we have something called dark matter, dark energy, and all that. Someone was talking about unable to detect, not being able to detect certain particles.
Yes, sir.
Yeah, and I'm not sure if you were going there, but there are particles, that's called dark matter. We don't know what they are. No one knows, but they seem to exist. About 70% of the universe is filled with dark matter. Only 30% is visible. So it's a huge fraction, huge chunk of the universe is dark matter, and they're not uniformly distributed either. So we don't know what is going on. We don't know what these particles are. People are trying to find out, but because they don't interact with anything, we cannot find them out. They don't emit light, they don't absorb light. So we don't know what is going on, but they are affected by gravity. Okay, so dark matter does seem to impact gravity. That's how we know that they exist. Okay, so yeah, as you say, this is a possibility that these dark matter have no resonances for any electromagnetic radiation at all. Okay, that's why we can't find them. Okay, maybe there is some other interaction, some other degree of freedom that makes them visible. We don't know that yet. Okay. Yeah.
Dark matter is like it will consume the matter, like for positive matter or the matter which is around us.
No. It does not consume. That is that is antiparticle. You're talking about antiparticles, particles and antiparticles. The universe has far less antiparticles that people don't know. People still don't understand why. Why do we have more particles than antiparticles? We don't know answer. We don't have an answer to that yet. But dark energy.
So we just name it, and then research going on.
No, it's not naming. We know that antiparticles exist. We can create them in lab. Okay, we can create positrons in lab. Okay, electrons and positrons. We can do that. Okay, we know that they exist.
But we don't know the properties where they can.
No, we know the properties of the antimatter also, not of dark matter. We know the properties. We know very well the properties of dark antimatter. Antimatter is very well known. We know that. What we don't know is why there is so much less antimatter. We don't have as many antimatters. Basically, if the universe is created evenly, there has to be half antimatter and half matter. Okay, but that doesn't seem to be the case. Okay, the case is like it's mostly matter, very less antimatter. Why is that? Nobody knows. Okay, but dark matter is a completely different story. Dark matter has been, hypothesized only now, only in the last maybe 30, 40 years. That is from that is by calculating the expansion rates of the universe. Okay, if there is no dark matter, the universe would be expanding faster. Okay, the expansion rate of the universe does not match the amount of mass that exists within the universe. This is from Einstein's general relativity equations. Okay, so you have to posit that there is more matter somewhere. Okay, if you look at a galaxy spinning, right, the galaxies are spinning perhaps faster than they should, or perhaps slower than they should, because if you can calculate the amount of mass in the galaxy by looking at the stars, by calculating the mass of the stars. You can do that very reliably these days. Okay, and when you calculate that, you see that the galaxy is perhaps rotating slowly, and that does not obey physical laws like conservation of angular momentum, let's say. Okay, then you have to posit that there exists more mass than meets the eye. Okay, that's dark matter, and this happens with a lot of galaxies. Yeah.
So you are saying that like dark matter hinders the expansion of the universe.
Dark matter actually changes the dynamics of galaxies. Okay, dark matter actually
Like
changes
by
the
dynamics. By dynamics, what do you mean? Like
by dynamics, I mean the frequency of rotation. Let's say you have two particles. Let's say you have two particles, M1 and M2. Okay, in space, they are gravitationally attracted to each other, and they are moving around each other. Okay, they are it's like sun and moon, sun and earth, right? They are rotating.
binary star.
Yeah, I'm sorry.
Binary star, sir. Binary star kind of.
Yeah, it's like a binary star. You can think of it as a binary star, right? So you know the mass of this object, you know the mass of this object, let's say, okay? And then now you can actually calculate how fast these things should be oscillating, right? You can do that. If you know the distance between these two objects, you can actually calculate how fast they should be moving if they have to be stable. Otherwise, they would fall into each other due to gravitational attraction. And if they don't fall into each other, that means they have to be oscillating or rotating at a specific frequency, specific periodicity, right? And if you observe the periodicity, and if it does not match the masses, what do you do? What do you do? Then you posit that there must be some other mass around it, around one of these or both of these, that is adding the mass, that is changing the dynamics. Okay, that is exactly how this dark matter has been posited. I mean, it is proposed. Nobody has observed what it is. Nobody knows what it is. Okay, but this changes the dynamics of the galaxies quite spectacularly. Okay, and this also affects the expansion of the universe, which is basically measured using a thing called a Hubble constant. And measuring the Hubble constant is basically one of the holy grails of astronomers these days. Okay, all astronomers, and I wouldn't say all, most of the astronomers are interested in what this Hubble constant is, how fast the universe is expanding. Okay, and apparently nobody knows. There are two answers to this, two numbers that people get depending upon their experiments. People don't know why they get two different numbers with different experiments. It's a big mystery. Okay, in astronomy. But the universe is expanding, all right. It is expanding. It is expanding, and the expansion rate is dictated both by dark energy and dark matter. There is dark energy also. Okay, and that actually helps speed up the expansion, whereas dark matter decreases the expansion. Okay. So
even
yeah,
wormholes do exist.
I'm
You
sorry.
have heard wormholes. Do they
Black
really
hole,
exist? No, so
black
wormholes.
wormholes. Okay. We don't know. No, we don't know that. We don't know that. Those are exotic solutions to general relativity equations. Those solutions are exotic. We don't know that yet. They may exist. We don't know that. Okay, and they exist. Uh, if the universe is flat, then they cannot exist. Okay, if the space-time fabric is flat, they cannot exist. But if the space-time fabric is bent like this, okay, then there is a possibility that you can go from here to here through a wormhole, meaning that
Yes,
this is
sir.
space-time, so you have to travel this far, but then you can take a shortcut through this. Okay, but is it really bent? Is the space-time bent like this? We don't know that. Okay, is the space-time a flat sheet or is it a bent sheet? We don't know that. And this scenario seems to be quite improbable. This kind of bent space-time, it does look improbable. Okay. 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 Any other questions? Okay, let me stop sharing and stop the recording.